Welcome to this session of Applied Animal Feeding. Today, this video is going to be an introduction to ration formulation and that math that's involved in ration formulation itself, and kind of the overview and a background on how we determine how much of each feed goes in to solve for any given requirement or goal that we're trying to solve. And so we need to think about a few things conceptually before we get started with actual problems. And so let's first define ration formulation. This is where, multiple feeds are blended together to meet a specific goal or requirement for an animal. I'm going to abbreviate requirement. And so we're taking feeds A, B, C, whatever the case may be, and trying to meet a certain requirement. And so those requirements can vary depending on stage of production and all the things we may have discussed in some previous videos. And so stage of production, your goal, all of those things can come into play. Visually, if we're going to represent ration formulation, we're going to be taking some amount. We don't necessarily know what amount of feed A, and we're going to be adding it to some amount of feed B. Together, those two amounts of each feed should equal, in this case, this is a 2-ingredient, the final ration that meets a goal. And so that is how we're going to be working through this ration formulation. Now, understand that we're doing some very simple 2 to 3 ingredients and solving for only one nutrient. We'll learn more in this series down the road about solving for multiple nutrients, but this video is specifically going to be only solving for one goal at a time. But it's to understand a little bit about the mathematics involved behind the scenes of how we do this. So our biggest challenge for solving these rations, like solving this ration here, is we do not know the amounts of the feed. So that's what we have to figure out, is how much of feed A, how much of feed B go together to create this final ration. And so if we kind of come back to this visual and keep that in mind, we could call feed A X as a variable. We could call feed B Y, and we know that those equal 100% of a ration. So mathematically, we could have X plus Y equals 100% of the ration. Now we can do something with this. So we need to solve for one of the two. In this case, we're going to solve for Y. Why? Because we need to. Sorry, couldn't resist. So the first thing is going to be to subtract X from both sides. So we're going to have X plus Y minus X is going to be equal to 100 minus X. So we will wind up with Y being equal to 100 minus X. Just a reminder, in this problem, X's will cancel out, leaving Y. So we have y equals 100 minus x. So we can have two unknown variables. We can have x and 100 minus x. These are the variables that will represent our unknown amounts of feed. Represent, spelling today, I think every day. The unknown amounts of feed. So we can now assign one of these feeds to be x, one of these feeds to be 100 minus x, and those amounts will give us the total ration. And now we can use that information to be able to solve a ration. So how would we apply this? Let's look at an application of this knowledge. Say we are asked to balance a ration for 70% TDN, total digestible nutrients. And that's going to be on a dry matter basis. That's our goal. We are to use steam-rolled barley and cottonseed hulls. To balance this ration. So now we know the two ingredients and our goal. However, we need to still apply our basic steps. Step 1 is going to be gather information. So we need to know how much TDN is in each of these two feeds. So we have our barley, that's steam rolled, I'm just going to abbreviate, and we have our cottonseed hulls. And so if I look these up on my feed library, or wherever you look up your feeds, I find that steam-rolled barley has 84% TDN. If I look up cottonseed hulls, it has 45% TDN. Now, a quick check to see if your ration or if this problem is even solvable is that your goal has to land somewhere in between these two numbers. So 70 is in between 84 and 45. If it wasn't, for example, if this number was 90, we could not solve this ration because there's no way, it has to be within the range. So the next step is to identify X. And as a result, we're also going to identify 100 minus X. So our second step is to identify X. And we're also going to be identifying 100 minus X as well. So our two variables. Okay, there's a rule. The feed with the highest concentration of the nutrient we care about, that nutrient of interest, or what our goal is, that is going to be equal to X. So if we look at barley and cottonseed hulls, we see that barley has the highest amount of TDN. That will be X. We also see that, so that only leaves cottonseed hulls to be the 100 minus X. And these values are going to represent the amount of each of these two ingredients in this ration. So our third step is to apply a math principle that has been in this series before, is when we take the amount of a feed times its nutrient concentration, in this case, it'll be the percentage of TDN, we're going to get the amount of a nutrient. And so if we figure out how much of a nutrient's coming from barley, how much of the nutrient TDN is coming from cottonseed hulls, if we add them together, they're going to have to equal 70%. So how do we do that mathematically? We're going to build an equation. So we're going to take our 70%, and that is going to be equal to the amount times the nutrient. So in this case, remember we can put the X on either side, but our nutrient concentration is going to be on the decimal form. So 0.84X plus 0.45 times 100 minus X. This is the barley. This is the cottonseed hulls. So mathematically, we have taken the amount and the nutrient concentration and we're multiplying them together. We're taking the amount and the nutrient concentration and multiplying them together. That gives us our equation to start. So step 4 is to solve the equation. So I'm going to take 70, I'm just going to rewrite it so we're clear on where we're at. And I'm going to be doing pretty much every step. And some can shortcut, your choice, but let me just walk this out for those that need it walked out. Not a problem at all. So the first thing we're going to do is distribute. Okay, so that means that we're going to take 0.45 times 100 and 0.45 times minus X. So that's going to give us 70 is equal to 0.84X plus 0.45 times 100 minus 0.45X. And we have to remember that this negative sign, this minus sign, goes with X. Okay, so now we're going to combine like values. Okay, so what we mean by that is I am going to subtract 45 from both sides because this is a whole number, this is a whole number. We also can combine these terms. I kind of split this into 2 steps just to make sure we can follow it. So 70 minus 45 is 25, and that's going to be equal to 0.84X minus, negative sign goes with X, 0.45X. If we combine these like values, we will get that 25 is equal to 0.39x. 0.84 minus 0.45. And just to clarify, I'll just plug it in. 0.39, that's where that number is coming from. Now we're going to isolate X. We can now solve for X, dividing both sides by 0.39. That cancels, leaving X equal to, let's plug it in, 0.25 divided by 0.39, 0.6410. Let's do that again. So let's solve for X. Let's take 25 divided by 0.39. That gives us 64.10. So X is equal to 64.10% of the ration. Now we also have to solve for 100 minus X. So what is 100 minus 64.10? That is 35.90%. And if we go back to, we have to remember that X represents barley. So the 100 minus X represents the cottonseed hulls in this problem. And that's how we can mathematically solve for two unknowns and solve to blend these ingredients into a specific amount that should meet this goal. In fact, let's go ahead and do a check. I'm going to add step 5 here, and let's check it, where we just plug it into the equation. So 70 equals 0.84 times 64.10 and plus 0.45 times 35.90. Okay, so if we plug this in, 0.84 times, get my numbers right here, 64.10, and actually I'm going to go ahead and declare that and put the parentheses in, just so we're clean about this, plus 0.45 times, actually, just 35.90. Okay, so I have it set up in my calculator to be the amount of TDN from the barley plus the amount of TDN from the cottonseed hulls. When I hit enter, it should be 70%. So that is rounding up to 70. That checks. So we have now just solved a ration that we didn't know the amounts for to meet a specific goal. Now, never is it as simple as two unknown ingredients equaling one thing. Sometimes in nutrition, we deal with what's called a fixed ingredient. And that means the amount is set, never changes. And so we need to account for it in the ration because it takes up space and may or may not supply the nutrient of interest, but we've got to account for it. And so it must be accounted for. So let's take a look at an example. We're going to balance a ration for 52 megacalories of net energy for maintenance per hundredweight or per counterweight per 100 pounds on a dry matter basis. So that's our goal. We're going to use the steamrolled barley that we had in a previous example and early bloom alfalfa hay. The new twist to this problem is, like, say if we were creating this ration for growing lambs, ammonium chloride is often fixed at 0.5% of the dry matter to prevent urinary calculi. So this is an example that would have a fixed ingredient. And we're going to learn that it does not supply energy, but it does take up space. So we need to account for it. So if we do the visual example again, I like thinking like that. It helps me to picture what's happening. So we have this ration, okay, that is going to be 100% of the dry matter, final ration. We know that a small amount, 0.5%, is ammonium chloride. But that leaves us with what we call slack space. So our other two ingredients, they're really not fitting into 100% anymore, are they? We actually only have, in this example, 99.5% of the remaining dry matter to use for our two ingredients. So that is important. So we have to account for the space this ammonium chloride takes up. Now, let's kind of reset, keep this visual in mind. We know that this visual is going to have some amount of barley and some amount of alfalfa. We just don't know how much yet. So let's gather information. Step 1, gather our info. So we have steamrolled barley. If I look it up in my feed library or whatever tool you're happening to use, I find out that it's 61 megacalories of net energy per maintenance per hundredweight. And then I look up the early bloom alfalfa and find out that it is 28 mcals of net energy per hundredweight. And I look up the ammonium chloride, and it is 0 mcals of net energy per hundredweight. It doesn't provide any energy. But does that mean we ignore it in our equation? Absolutely not. It's got to be in that equation. So we know, like if we were to determine the amounts, steamrolled barley is an unknown. Early bloom alfalfa is unknown, but ammonium chloride, up there, is 0.5% or pounds. So of these two feeds, steamrolled barley is the energy source. So that is going to be set to X. And then since we're not working out of 100% now anymore, we're now working out of 99.5% space. That is going to be the minus X. So instead of 100, it's now 99.5 because we know that these need to add up to 100 and that the ammonium chloride is taking up 0.5%. So now we can build our equation and solve. So we are looking at 52 mcals per hundredweight. I'm going to keep that on a hundredweight basis. And so we're going to need to determine the amount of megacalories. How many megacalories are coming from barley, alfalfa, and the ammonium chloride? And so we're going to take the decimal form. So this is per hundredweight. We're going to want to convert that to pounds. So we're going to move the decimal 2 points to the left. So that's going to be 0.61 times X. That's going to be our barley. We're going to add that to the amount of alfalfa. 2 decimal points to the left is 0.28 times 99.5 minus X. The alfalfa. And the ammonium chloride. It does supply 0, but it takes up 0.5%. So if you're just starting out, I would include it and write it in your equation. That way you can verify that you have all 3 ingredients that are required to be in a ration, or if there's more than one fixed ingredient, which can totally happen, that you've accounted for everything. And there are times when this other nutrient, this fixed nutrient, could supply the nutrient we need. So I always recommend we include it in our equation building to build a good consistent pattern with how we solve problems. So now we can start solving this. So let me just get that rewritten clearly. And let's distribute through the parentheses. So we're still going to be 0.61x plus 0.28 times 99.5. is 27.86 minus 0.28x plus 0. Okay, so now I can discount the 0. I'm okay with that. And so we need to subtract 27.86 from both sides and combine the x's. So let's start with 52 minus 27.86 gives us 24.14. And then if we subtract 0.28 from 61, 0.61 minus 0.28, we're going to get 0.33x. So we're just combining like terms, and now we can isolate x. So if we take the 24.14 divided by the 0.33, we get 73.15%. And if we recall, x is representing the barley. Now we're going to solve for 99.5 minus x, which was our second unknown variable. So 73.1, clear. So 99.5 minus 73.15. That's going to give us 26.35% alfalfa. Quick check, let's just add those two up, the barley and the alfalfa. And those equal 99.5. And then our last one is that ammonium chloride is 0.5%. And so we have solved a ration with a fixed ingredient. We've learned about slack space is the amount of space available in a ration for feeds to occupy. And that isn't always 100. That can be a variable number depending on the ration you're solving. So that is how we solve a ration using a fixed ingredient. So that's the basics of some mathematics that goes into solving for rations. There's a lot of basic algebra in the background. Who knew you might use algebra again? And while when they get into the programming and the big software packages, it's all linear programming and a lot of other things going on. But this is the basics to start understanding how we can start solving rations and balancing for rations in a simple setting using a handful of feeds and solving for one specific goal. Thanks.